Imagine for a moment that the universe, with all its galaxies, black holes, and quantum particles, doesn't actually exist when no one is looking at it. This isn't science fiction. It's biocentrism, a revolutionary theory suggesting that consciousness itself creates reality, not the other way around. According to biocentrism, developed by scientist Robert Lanza, life and biology are central to existence, not mere byproducts of physical processes. The universe itself emerges from our perception. Without observation, the cosmos exists only as a field of probability. The double-slit experiment shows that particles behave differently when observed, existing as waves of probability until measured. But biocentrism takes this further, suggesting the entire universe behaves this way. Space and time themselves may be tools of our consciousness, mental constructs we use to organize experience, rather than fundamental aspects of an external reality. This could explain quantum entanglement, where particles instantaneously affect each other across vast distances. They're not breaking the light-speed barrier. They're connected in a deeper reality, where distance is an illusion created by our perception. The implications are staggering. If consciousness shapes reality, then the death of the observer becomes impossible in the conventional sense. Consciousness may be immortal, shifting perspectives rather than ending. The universe is fine-tuning for life, those precise physical constants that allow for our existence, takes on new meaning. Perhaps the constants are perfect for life, because life itself shaped them through observation. Some scientists dismiss biocentrism as pseudoscience. Others see it as the natural evolution of quantum theory, the missing link explaining why quantum mechanics seems so counterintuitive. Could our cosmic observations, from telescopes peering into deep space to particle colliders smashing atoms, be creating the very phenomena we're studying? And the most unsettling question, if observation creates reality, what happens to the parts of the universe no one is looking at? This isn't just about physics anymore. It's about the fundamental nature of existence itself. What if we are not just in the universe, but the universe is in us? Have you ever stared into the night sky and wondered what lies between the stars? Not just darkness, but true emptiness. Now imagine discovering a region so vast, so astonishingly bare, that it seems to violate everything we know about how the universe works. This is the Boötes void, sometimes called the Great Nothing. It's one of the largest and most haunting cosmic voids ever discovered, and it's unlike almost anything else in the observable universe. Take a breath, because what you're about to hear may change the way you think about the structure of reality. The Boötes void spans a staggering 330 million light-years in diameter. That's not a typo. 330 million. It was first discovered in the 1980s during redshift surveys, observations that map out the distances and velocities of galaxies across space. Astronomers were charting the cosmic web when they noticed something strange. A huge, empty region where galaxies should be. It wasn't just underpopulated, it was nearly abandoned. In a universe that resembles a tangled web of galactic filaments and clusters, the Boötes void is like someone punched a hole straight through the cosmic fabric. Now, to be clear, voids themselves are normal. Cosmic evolution naturally creates pockets of low-density regions between galaxy-rich filaments. But even the most sophisticated models, like the Lambda CDM model, which governs our current understanding of the universe, do not predict voids this large or this empty. Within the Boötes void, there should be thousands, tens of thousands of galaxies, but there are only a few dozen. It's as if an entire chapter of cosmic formation just didn't happen. Why? One explanation is that this void is the result of quantum fluctuations in the early universe. Tiny irregularities, multiplied by inflation, could have left behind immense regions where matter simply failed to gather. Another theory is that gravity pulled matter more aggressively toward nearby filaments, squeezing galaxies into tight clusters and leaving behind what appears to be an oversized gap. But those explanations are far from complete. Because the Boötes void doesn't just defy where matter went, it challenges how matter behaves at all. Some researchers have floated more exotic ideas. What if dark matter behaves differently in these regions? Or worse, what if some other force, some unknown property of the universe, actively prevents matter from forming in these zones? There's even speculation that some voids may result from interactions with topological defects, strange features left behind by the universe's earliest phase transitions, like cosmic strings or domain walls. And there's a deeper implication. What if regions like the Boötes void are more than just random absence? What if they're structured absence? Patterns of non-structure, embedded within the overall design of the universe. It makes you wonder, could this be a scar left behind by something we don't understand? A silence in the symphony of creation? Take a moment to reflect on this. A region more than 300 million light-years wide, almost completely devoid of galaxies, staring back at us like a black eye in the cosmos. We map galaxies, we name constellations, we marvel at what is there. But the Boötes void reminds us of what's not there, of the profound power of absence, and of how little we still understand about everything. What other gaps are hiding in the sky? What else has the universe quietly left out? Pause. Breathe. Somewhere, in the deep black silence between galaxies, a whisper becomes a scream. It lasts just a fraction of a second. And yet, in that blink of time, it releases more energy than the sun emits in days. We call them fast radio bursts, but what they really are is still unknown. They arrive without warning. Brief pulses of radio waves, sharp, bright, and unexplained. Some come from distant corners of the universe. Others repeat as if something is trying to speak in a language we haven't learned to hear. The first FRB was discovered in 2007. A strange anomaly hiding in old data. A burst that should not have been there. It came from billions of light years away, and then it vanished. No follow-up signal, no clear origin, just a blip. Since then, hundreds more have been recorded, some only once, others again and again, repeating like pulses from a lighthouse we can't locate, and some follow no pattern at all. Where do they come from? Astronomers have tried to answer this with known physics. Some suggest magnetars, neutron stars with impossibly strong magnetic fields, flaring with bursts of radio energy. Others point to more violent events, supernovae, black hole mergers, collapsing stars. But those explanations falter when we consider the repeaters. If FRBs were simply the death cries of cosmic giants, why do some occur again and again, like a signal that never tires? In 2020, scientists traced one FRB to a magnetar within our own galaxy. It was the first real connection, confirmation that at least some bursts might be natural. But that magnetar was close, and most FRBs don't come from within our galaxy. They arrive from deep intergalactic space, places with no visible galaxies, no clear energy sources, just darkness. Which raises a deeper question. What if these bursts are not accidents? What if, somewhere out there, something intelligent is using energy in a way we don't understand. A propulsion system, perhaps, blasting bursts of radiation to move through space, or a form of interstellar communication, or something else, something we have no frame of reference for. The Breakthrough Listen project, one of the most serious scientific efforts to detect alien techno-signatures, has considered this. They don't claim FRBs are alien signals, but they've asked the question. And that, by itself, is telling. Because we don't know what's out there. And if even one FRB came from an artificial source, then we are not alone. But even without that leap, FRBs remain a cosmic riddle. They are bright, fast, and coldly indifferent. Each one is like a knock on the door from nowhere. And by the time we answer, it's already gone. We are listening, but we do not know who or what is speaking. And in the silence that follows, we are left to wonder. Not all mysteries are made of shadows and emptiness. Some come in flashes, so quick, so bright. They leave no trace at all. And yet, they linger, like echoes from a mind we have never met. In 1977, a sound came from the stars. It lasted just 72 seconds, a burst of narrowband radio energy, powerful, clean, and unexplained. It arrived without warning and was never heard again. An astronomer named Jerry Eman, reviewing the printed data, circled the signal's numbers and wrote a single word beside it. Wow. And with that, one of the greatest space mysteries was born. We now call it the WOW signal. It came from somewhere near the constellation Sagittarius, deep in the sky, far from anything we can see with the naked eye. More precisely, it originated near the star group Chi Sagittarii, approximately 2.5 degrees south of the fifth magnitude star group. The frequency? 1,420 megahertz. That may sound arbitrary, but it's not. It's the frequency of neutral hydrogen, the most abundant element in the universe, and perhaps the most logical frequency to use. If you wanted your signal to be noticed by someone intelligent, many scientists believe alien civilizations would choose this frequency. Universal, neutral, obvious. The perfect cosmic calling card. That's exactly where the WOW signal was found. And then it vanished. No second signal, no echo, no follow-up, nothing. The Big Ear Radio Observatory in Ohio, where the signal was detected on August 15, 1977, scanned the same part of the sky again and again. No repetition. No error was ever found. No known satellite, comet, or Earth-based reflection matched the signature. This wasn't just static. It was narrowband, focused, isolated, exactly what intelligent life might send. The signal was 30 times stronger than the background noise of space. The printout showed a sequence, 6EQUJ5, representing the signal's intensity. It reached its peak at U, 30 times stronger than the cosmic background. Some have tried to explain it. Comets passing through. Unusual natural sources. Transmission leakage from Earth. But every explanation has a flaw. None account for what was recorded that day, and why it happened only once. Which leads us to the possibility many are reluctant to say out loud. That it wasn't an accident. That it wasn't natural. That it was a message from someone or something. Maybe a misfire, a test, a flare from a dying world, or perhaps meant for someone else entirely. And we just happen to be in the way. We don't know. We may never know. But for 72 seconds, the full duration, the telescope was pointed at that region. Humanity may have caught a signal, clear, strong, and intentional. The silence that followed is what makes it so haunting. as if the universe opened its mouth to speak, and then closed it again. We've pointed our dishes back to the stars. We've listened. We're still listening. But the wow signal remains a singular event, not a conversation, not even a sentence. Just one word, one note, one moment, and then quiet. Sometimes, what's most unsettling is not what we hear, but what we don't hear. In late 2017, something entered our solar system. It wasn't a comet, it wasn't an asteroid, and it wasn't from here. It came in fast, on a hyperbolic trajectory, meaning it was not bound to the sun. It would pass through once and never return. We named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. But we still don't know what kind of messenger it was, or what message, if any, it carried. This was the first time humanity had ever confirmed an interstellar object moving through our solar neighborhood. A visitor from another star system, cutting through space with strange motion and stranger features. From the moment it was detected, Oumuamua didn't behave like anything we'd ever seen. It had no visible tail, no trail of gas or dust like a comet. It didn't flash or flare. And yet, it accelerated slightly as it exited the solar system. That tiny increase in speed shouldn't have happened. At first, scientists assumed it was caused by outgassing, gases released by the melting of ice as it passed near the sun. But there was no visible gas, no debris, nothing to suggest a natural release of energy. And its shape was unlike anything in our planetary catalogue. Estimates suggested it could be extremely elongated, like a cigar, or unusually flat, like a pancake. It rotated end over end every 8 hours, tumbling chaotically, as though it had been drifting through space for an eternity. The more we looked, the less we understood. One theory emerged, quietly at first, then louder. Solar radiation pressure, the force of sunlight itself, might have been enough to account for its odd acceleration. But that would only work if the object were very thin, like a sheet or a sail. A light sail, a concept we've imagined for our own interstellar travel. Thin, reflective material, pushed by starlight over time. No fuel, just light and motion. If true, this would mean Oumuamua was not a rock, not a relic, but a craft. One astrophysicist, Avi Loeb, stepped forward with that bold idea. What if this was a probe? An ancient artifact from an advanced civilization, designed to drift between the stars, silent and slow, collecting information or simply passing through. The scientific community responded with caution. Many disagree. No proof, no direct evidence, too many assumptions. And yet, no natural explanation fits all the data either. It came, it moved, it changed speed without visible cause, and it left. That is what we know. And in that ambiguity is a kind of cosmic discomfort. Because if Oumuamua was natural, it challenges what we thought we understood about the objects beyond our solar system. But if it wasn't, then it wasn't alone. Someone, or something, sent it. Maybe eons ago, maybe no longer watching, or maybe always watching. Since then, more interstellar visitors have been detected. 21b Borisov, for example, but it looked like a typical comet. Predictable, explainable. Oumuamua was neither. It came without sound, without warning, and without leaving a single, clear answer behind. A silent shape from between the stars, tumbling through space, accelerating, and then disappearing into the dark. Whatever it was, it didn't stay, and we weren't ready. Most stars behave as expected. They shine steadily, burning across the darkness with predictable rhythms of physics. Their pulses are known, their cycles, measured. But then there's Tabby's star, a star that refuses to follow the rules, a star that flickers, doctor and sometimes nearly disappears. Located in the constellation Cygnus, officially known as KIC 8462852, but most know it as Tabby's star, named after astronomer Tabitha Boyajian, who brought it to global attention. In 2015, volunteers examining Kepler's Space Telescope data noticed something strange. The star's brightness dropped, not just by a little, but by up to 22%. And it didn't do it once. It happened again and again, irregularly, without any clear pattern. These dimming events didn't behave like planetary transits, and it wasn't a binary star system either. Whatever caused the flicker was neither round nor consistent. At first, astronomers looked for simple answers, a swarm of comets perhaps, or maybe interstellar dust, creating the illusion of dimming. But there were problems with those ideas. The dips were too deep, too erratic, too long-lasting. And when scientists looked at historical data, they found something even stranger. The star had been slowly fading for decades, a trend that no known dust cloud or comet swarm could explain. So the theories grew stranger, and one changed everything. A small group of researchers suggested the unthinkable, that we might be witnessing the construction of a Dyson swarm, a structure built to surround a star and harvest its energy. Something artificial, something massive. This wasn't science fiction. It was a real peer-reviewed suggestion, published by respected scientists, acknowledging that all natural explanations had failed. Of course, it's just a theory, a placeholder for the unknown. But it was the first time a mystery in astronomy was so strange. That intelligent design couldn't be ruled out outright. And that is unsettling, because the universe is vast and ancient and quiet. So when a star misbehaves, and we listen, and still hear nothing, we are left with two possibilities. Either it's something new in nature, something we've never seen before, or it's something built, something left behind, something still in progress. We've aimed radio telescopes at Tabby's star, listened for signals, looked for motion, heard only silence, but the light keeps dipping, a flickering candle in the cold wind of space. Maybe it's a rare kind of dust. Maybe it's ancient debris. Maybe it's something natural, subtle, and new. But maybe it's not. Maybe something is happening out there. A project, half-finished. A structure, incomplete. A civilization, just on the edge of our perception. And whether natural or artificial, the mystery remains. A star that dims without warning, refuses to explain itself, and vanishes, bit by bit, into the dark. When we think of planets, we imagine order, worlds bound to suns, tracing familiar paths in elliptical orbits, anchored, warmed, and lit. But not all planets are loyal. Some are lost. These are the rogue planets, alone, wandering, drifting through space without a star. They do not orbit. They do not shine. And they are far more common than we once believed. Rogue planets, also called interstellar planets, are planetary mass objects that have been cast adrift. Some may have formed like stars, collapsing from clouds of gas without ever igniting. Others may have once belonged to solar systems, before being flung into the void by violent gravitational encounters, slingshotted into oblivion by larger planets, or displaced by a passing star. And now they wander. They are invisible to the naked eye, difficult to detect even with our best instruments. They reflect little light, They emit almost none, and yet they are out there. Estimates suggest that for every star in the Milky Way, there may be 2 rogue planets, possibly more. That means hundreds of billions of worlds, sailing alone, without orbit, without light, without home. Some are giants, cold, bloated gas spheres. Others may be rocky, Earth-like, ancient and frozen. And while the darkness seems absolute, not all is lifeless. Some rogue planets may have internal heat, generated by radioactive decay in their cores or friction from past tidal forces. This heat could be enough to maintain subsurface oceans shielded beneath thick layers of ice, entire ecosystems hidden from the stars, life sustained not by sunlight, but by geology. Imagine an ocean world, trapped beneath an icy shell, wandering between galaxies, untouched for billions of years, its surface frozen, its heart warm, no sunrise, no sky, just an endless night, and something swimming in the dark. Rogue planets stretch our definitions. What is a planet if it does not orbit a star? What is a system if it has no center? These worlds challenge what we thought was normal, and they remind us that space is not only vast, but unbound. Some rogue planets may be ancient, older than Earth, older than the Sun, relics of forgotten systems, ghosts of long-collapsed stars. Others may still be young, freshly torn from their orbits, set adrift by chance. Some may have moons, atmospheres, ruins, or memories of life that once was, and others may still harbor life now, deep within, hidden, waiting. Take a moment to imagine the silence of such a world. No day, no night, just darkness, forever. These are not planets in the way we understand them. They are wanderers, pilgrims through space, planets with no star and no destination. And they are out there, all around us, moving silently, without orbit, without light, and perhaps without end. Everything in the universe moves. Stars orbit stars, galaxies spiral, clusters drift. Even our own Milky Way is not stationary. It's in motion. But where is it going? And more importantly, why? For decades, astronomers have tracked the movement of galaxies across the sky, and they noticed something strange. A subtle flow, a drift, pulling entire galaxies, including ours, toward a specific region of space. That region lies in the direction of the Centaurus and Hydra constellations, and whatever sits there is exerting enough gravitational pull to draw in thousands of galaxies, including our own. This mysterious force has a name. We call it the Great Attractor. And what makes it so deeply unsettling is that we can't see it. Our entire galaxy is moving toward it at over 600 kilometers per second. That's more than 2 million kilometers per hour. Not a gentle drift, but a cosmic acceleration towards something invisible, something powerful, something unknown. This anomaly lies roughly 150 to 250 million light-years away, but it's hidden behind one of the most difficult observational obstacles, a region called the zone of avoidance. That's not metaphor. It's a literal part of space where the dense plane of our Milky Way, filled with stars, gas, and dust, makes it nearly impossible to see beyond. Even with infrared and X-ray telescopes, our view is limited. We can detect hints, shadows, gravitational effects, but we still can't see the thing itself. So what is it? One theory suggests it's a supercluster of galaxies, an immense concentration of mass hidden behind our line of sight. Another points to dark matter, which might account for the gravitational pull without being visible in any spectrum of light. But the deeper we look, the weirder it gets. Some astronomers believe the Great Attractor might not even be the end of the story. They propose that it's merely one part of an even larger structure, the Shapley supercluster, or perhaps something grander still, a gravitational current flowing through the cosmic web, one that we're caught in, one that's pulling us, gently, constantly, towards something beyond. We tend to think of space as static, but in truth, we are all in motion, not randomly, not aimlessly. Something is pulling us, and we do not know what. It is massive, it is invisible, and we are heading straight toward it. In the end, perhaps the greatest mysteries aren't those we reach out to find, but those that are already reaching for us. At night, we look up at the stars and feel it, the vastness, the possibility, the question. Are we alone? With hundreds of billions of stars in our galaxy alone, and trillions of galaxies beyond, the math seems clear. We cannot be the only ones. This is the paradox that haunted physicist Enrico Fermi. Where is everybody? He asked. A simple question with unsettling implications. Our galaxy is ancient, over 13 billion years old. If a civilization arose just millions of years before us, they would have had time to spread across the stars, to build, to explore, to make themselves known. Yet we hear nothing. A silence so complete, it demands explanation. Some say they're out there, but we're not listening correctly. Perhaps their signals are too alien for us to recognize. Or maybe advanced civilizations communicate in ways we can't detect, using quantum entanglement or channels we haven't discovered. Others suggest a darker possibility, the Great Filter hypothesis. Something prevents civilizations from reaching the stars, a hurdle so insurmountable that none survive it. Nuclear war, artificial intelligence, environmental collapse, or something we haven't yet faced. Perhaps life itself is rarer than we imagine. The delicate chemistry of consciousness, more precious than gold in this cold universe. Or maybe they're hiding, watching us from afar, waiting for us to reach some cosmic milestone before making contact. The most haunting explanation is the simplest. We are alone. The first, the only, the exception, carrying the torch of consciousness in an otherwise dark cosmos. We send our signals outward. We point our telescopes to the stars. We listen for the faintest whisper. And still, only silence answers. This is the weight of the Fermi paradox. Not just a scientific question, but an existential one. In the endless quiet of space, we face ourselves and wonder if the silence is our future too. We've all heard of black holes, cosmic pits where gravity is so intense not even light can escape, where time slows and eventually stops, where matter is consumed, compressed, erased from the visible universe. But what if there was something else, something just as strange, but moving in the opposite direction, something that doesn't pull matter in, but hurls it out? Welcome to the concept of the white hole. Theoretical, unconfirmed, but hauntingly possible. A white hole is not a creation of science fiction. It falls straight out of the equations of general relativity. The same mathematics that predicted black holes also predicts their mirror image. In a white hole, nothing can enter, but everything, matter, energy, light, can escape. A one-way door, not into darkness, but from it. In classical physics, white holes are considered unstable. Any matter attempting to approach would disrupt their perfect boundary, causing them to collapse or behave unpredictably. And yet, in the strange blend of relativity and quantum theory, the idea has never fully disappeared. In recent years, developments in loop quantum cosmology, a model that attempts to unify quantum mechanics with gravity, have given white holes a second life. Some physicists now believe that black holes could eventually transform into white holes. Here's how. Over time, a black hole slowly radiates energy through a process known as Hawking radiation. This evaporation is incredibly slow, but as the black hole shrinks, some theories suggest it could bounce, flipping into a white hole and releasing its contents back into space. A slow death, followed by a final burst, a cosmic rebirth. In this model, a black hole doesn't just erase information, it stores it and returns it. This might help resolve one of the most troubling paradoxes in physics, the black hole information paradox. Because according to quantum theory, information cannot be destroyed, but if it falls into a black hole and disappears, where does it go? A white hole could be the answer, a release valve, a correction, a way for the universe to stay honest with itself. And there's another idea, one even stranger. Some physicists propose that every black hole could be connected to a white hole in another universe. A wormhole, a bridge, a passage between space-times. What we see as the end might be the beginning, somewhere else. In this view, the Big Bang itself could have been a kind of white hole, not just an origin, but an exit, a massive explosion of energy and matter, emerging from the death of a black hole in a parent universe, a cosmic recycling. One universe collapses, another bursts into being. If that's true, then our universe didn't just begin. It was expelled from a singularity, from darkness, from something we can't yet see, but may one day understand. White holes are more than mathematical curiosities. They are mirrors. They challenge what we think we know about space, time, and causality. A black hole says, "Come no closer. You cannot return." A white hole whispers, "I cannot take you in, but I can show you what lies beyond." And somewhere, folded into the distant fabric of space-time, there may already be one, waiting, expanding, releasing, not a trap, but a door that only opens out. Black holes are not rare. We've found them scattered across space, born from dying stars, lurking in the hearts of galaxies, bending light and swallowing matter. But when you look closer, a strange silence emerges, because between the smallest and the largest black holes, there's a gap that shouldn't exist. We have stellar mass black holes, typically between 5 to 100 times the mass of the Sun, formed when massive stars collapse under their own gravity. We also have supermassive black holes, millions to billions of solar masses, anchored at the centers of nearly every galaxy, including our own. But in between, where we expect to find thousands of mid-sized black holes, we find almost nothing. This missing population is what we call intermediate mass black holes, and their absence is a mystery. According to theory, these objects should exist. They're supposed to bridge the evolutionary gap. Small black holes merge and grow over time, eventually forming the colossal giants we see today. But if that's true, where are all the in-between ones? Why is the ladder missing its middle rungs? For decades, astronomers have searched, scanning star clusters, probing the edges of galaxies, studying X-ray bursts and gravitational waves. Hints have surfaced. In 2020, the event GW190521 was detected by LIGO and Virgo, an intense ripple in spacetime caused by the merger of two massive black holes. The final object landed right in the intermediate range. Was that our first solid proof? Maybe, but the data was faint, the interpretation contested, the debate ongoing. Other clues come from globular clusters, dense spheres of stars orbiting galaxies. Some of these clusters show signs of hidden mass, as if something heavy sits at the center, invisible, influencing the motion of nearby stars. But again, no definitive detection, no clear, repeatable signals. It's like chasing shadows in the void, and that silence speaks volumes. Because if intermediate mass black holes truly don't exist, it means something is wrong with our understanding of how galaxies form. It means supermassive black holes didn't grow through mergers at all, but instead formed through primordial processes, direct collapse from massive gas clouds in the early universe, or from exotic mechanisms we haven't yet imagined. Some have even suggested that dark matter played a role, guiding the birth of these giants through gravitational scaffolding invisible to our eyes. The stakes are high, because this isn't just about a missing object. It's about a missing chapter in the story of the cosmos. If we never find intermediate black holes, we may have to rewrite that story, change the way we think galaxies evolve, change the way we think the universe grows. But if we do find them, it could unlock secrets about the first moments after the Big Bang, about the building blocks of structure, about the hidden architecture of space itself. Sometimes, it's not what we observe that pushes science forward, but what we don't observe, what's absent, what refuses to be found. In space, even silence leaves fingerprints, and the quiet between two extremes may hold answers we've only begun to ask. Black holes are where the universe stops playing fair. They bend space, they freeze time, they swallow light, and once something crosses the event horizon, it's gone. But what if what's truly lost isn't just matter or energy? What if black holes destroy information? And if they do, then the laws of physics themselves may no longer apply. This is the black hole information paradox, one of the most profound puzzles in modern science. It began with a contradiction. On one side, we have general relativity. It tells us that anything falling into a black hole gets crushed at the singularity, gone, forever. On the other side, there's quantum mechanics. And in this world, information can never be lost. Every particle carries information, its position, momentum, quantum state. These two truths cannot coexist. And then came Stephen Hawking. In the 1970s, he showed that black holes aren't entirely black. They emit particles, a slow, cold glow known as Hawking radiation, over immense timescales. This radiation causes black holes to shrink, to evaporate, which means all matter and energy inside is eventually released as heat. But the information? That, Hawking said, is lost, erased. This idea shattered physics, because if information can be lost, then quantum mechanics fails. So, how do we fix it? Some physicists believe information is preserved, hidden in patterns within the Hawking radiation. Others suggest the event horizon acts like a storage device, recording everything in two-dimensional form. This gave rise to the holographic principle, the idea that all information in a three-dimensional space can be encoded on a two-dimensional boundary. Think of a black hole not as a bottomless pit, but as a cosmic hard drive that stores information on its surface. And then, there are stranger ideas. What if black holes send information somewhere else, through wormholes, across dimensions, or into new universes? In this view, information isn't lost, it just escapes us. And yet, no theory has been proven. It means we still live with a paradox at the heart of the universe, a standoff between the rules that govern the very large and the rules that govern the very small. Both work, both are tested, both are true. But in the presence of a black hole, they disagree. Until we solve that disagreement, our understanding of reality remains incomplete. Because if information can be destroyed, then time becomes irreversible. Causality breaks down. So we're left with a question. What happens to the story of a thing when its ending is erased? Does it echo? Is it stored? Or is it gone forever? In the shadow of a black hole, the universe writes in disappearing ink. From the outside, black holes are terrifying enough. They're invisible. They warp time. They trap light. But the real horror begins when you fall in. Approach the event horizon, and space itself begins to twist. Distances stretch, forces intensify, and gravity starts to do something truly disturbing. It doesn't just pull you in, it pulls you apart. This is the phenomenon scientists call spaghettification. Yes, spaghettification. It sounds cartoonish, but it's very real and utterly gruesome. It happens because of tidal forces, the same type of force that causes tides on Earth, created by the gravitational pull of the moon. Except, near a black hole, this difference in gravity becomes catastrophic. If you're falling feet first into a stellar mass black hole, the gravitational pull at your feet is far stronger than the pull at your head. The closer part of your body is accelerated more than the rest. The result? You begin to stretch vertically while being compressed horizontally until every part of you is pulled into a long, thin strand of matter, torn atom from atom, and eventually particle from particle. It's not instantaneous. It's progressive, and it's inevitable. A stellar black hole would turn you into a subatomic string long before you ever reach the center. But with supermassive black holes, the story becomes stranger. The event horizon of a supermassive black hole is farther from the singularity, and its tidal forces, while still extreme, are spread out more gently across that vast radius, which means you might fall in and feel nothing, at least at first. You could cross the event horizon without being torn apart. No alarms, no warnings, just a calm descent into something you can never return from. What happens next? We don't know, because no signal escapes a black hole. No data, no light, no story. Once you pass the horizon, physics goes dark. And yet, the questions get louder. If you're destroyed, if your particles are stretched into oblivion, what happens to you? Not your body, but your information, your quantum state, your memories, your identity. Are you truly gone? Or is something preserved? Are you stored, encoded, scattered, like static across a cosmic hard drive? Or are you erased? Your story ended at a point where time itself begins to dissolve. This is where space-time no longer behaves, where Einstein's equations start to collapse. And quantum theory doesn't know what to say. Some physicists believe the singularity isn't a thing at all, just a mathematical placeholder, a region where the known laws of reality surrender to chaos. Others think something else might happen, a folding of space, a tunnel to another part of the cosmos, a bridge to somewhere, or something else. But we can't test it, we can't observe it, and so we're left with theories and imagination. Falling into a black hole is not just a physical journey, it's a boundary, where knowledge ends, where certainty dies, and at that boundary, you stretch, you thin, you vanish. Spaghettification is more than a morbid curiosity. It's a symbol of how fragile physics becomes when pushed to its limits. A human being stretched across eternity, reduced to a thread, unwritten by gravity, a scream without sound, a question without answer, and a name that sounds absurd. until you realize it's the closest thing science has to describing what can't be described. Some stars burn, some stars collapse, but a rare few, shatter the rules. These are the magnetars, the most magnetic objects in the known universe, small, dense, unstable, and capable of breaking physics itself. A magnetar is born in violence, the remnant of a star that exploded in a supernova. What's left behind is a neutron star, a collapsed core, only about 20 kilometers across, but containing more mass than our Sun. A single teaspoon of this matter would weigh billions of tons. But some neutron stars don't just collapse, they twist. Under the right conditions, the magnetic field intensifies, far beyond what should be possible. And a magnetar is born. Its magnetic field can reach 10 to the 15th Gauss. That's 1 trillion times stronger than Earth's. So strong it can distort atoms, literally changing the shapes of matter itself. So intense, it could erase a credit card from halfway across the moon. These aren't just magnetic stars, they're magnetic monsters. And they don't just sit quietly in the sky. Magnetars quake. Their crust, if it can even be called that, bends under magnetic pressure. And sometimes it cracks. These starquakes release energy equivalent to billions of nuclear bombs. And when they do, the magnetar flares, blasting X-rays and gamma rays into space in all directions. In 2004, one such flare erupted from a magnetar 50,000 light-years away, and it still managed to disrupt Earth's ionosphere from across the galaxy. That same event was powerful enough that, had it occurred just a few dozen light-years closer, it might have wiped out our satellites, our power grids, even our atmosphere. They are small, they are rare, but they are not safe. Only about 30 magnetars have been confirmed in our galaxy. That might sound reassuring, but the truth is, we don't know how many more exist, quiet, waiting between stars. Their lifespans are short, their behavior unpredictable, their flares catastrophic, and some scientists now believe that magnetars might be responsible for some of the strangest signals we've detected from space, including the powerful, sudden bursts known as fast radio bursts, or FRBs. Others suspect that certain gamma-ray bursts, among the most energetic explosions in the universe, might also be the final death throes of a magnetar collapsing into something worse. And yet, we barely understand them. What keeps their magnetic field stable? What causes them to flare when they do? Why are they so rare and so violent? We don't have answers, only theories, only warnings. A nearby magnetar could, in theory, pose a planetary threat, emitting radiation strong enough to sterilize the surface of Earth, or fry our digital infrastructure in a matter of seconds. But more than their danger, it's their impossibility that captures the mind. These are stars that shouldn't exist, born in chaos, fused by pressure, and twisted by magnetism so intense it warps the very structure of reality. They are not large, they are not bright, but they are perfect storms of physical extremes, and they remind us that the most terrifying things in the universe aren't always the biggest. Sometimes they're the smallest, the densest, the most concentrated expression of power ever discovered. A dead star, reborn as a cosmic curse. What if the most dangerous substance in the universe isn't explosive, isn't radioactive, isn't even hostile? What if it simply exists, and by existing, it turns everything else into more of itself? This is the unsettling idea behind strange matter, a hypothetical form of matter so dense, so alien, that contact with it could trigger a chain reaction, one atom at a time, until everything you know, every planet, every star, every cell, becomes something else. Strange matter isn't science fiction. It's a serious theoretical concept in high-energy physics. And it begins with a question. What happens when you compress normal matter too much? Inside atomic nuclei, we're used to dealing with protons and neutrons, particles made of up and down quarks, held together by the strong nuclear force. But in extreme conditions like the core of a neutron star, something strange might happen. Literally, under enough pressure, protons and neutrons could break down, their internal structure reshaped. A third kind of quark, called the strange quark, emerges, and the result is something radically new, strange matter. In this state, atomic structure collapses. Matter becomes smoother, denser, more stable. So stable, in fact, that it might be more stable than ordinary matter. And that's where things get terrifying. Because if strange matter is truly more stable, then normal matter becomes unstable in its presence. That means a single strangelet, a tiny clump of strange matter, might, just by touching normal matter, convert it, one particle at a time, quietly, unstoppably. This hypothetical process is called strangelet conversion, and if it started, it wouldn't stop. The reaction would spread like a virus at the atomic level, tearing through the Earth, the Moon, the Sun, turning it all into strange quark material, and no force in nature could reverse it. No explosion, no warning, just transformation, total, irreversible, alien. Physicists studying particle accelerators have debated whether strange matter could form in high-energy collisions, like those in the Large Hadron Collider. Some even worried at first about an accidental doomsday. But so far, nothing. At least, not here. Still, strange matter could exist elsewhere, hidden in the collapsed cores of quark stars, hypothetical objects denser than neutron stars, where strange matter might form naturally. It could be out there already, drifting silently through the galaxy, a strangelet, small, cold, dark, passing through the void like cosmic pollen. And if one ever wandered into our solar system, we might not know. Not until atoms began to convert. Not until it was too late. But maybe it hasn't happened because we're lucky. Or maybe because strange matter is only created in the rarest, deadliest corners of space. But the fact remains, if it is real, then it could end everything. Not with fire, not with noise, but with inevitability. It doesn't explode, it doesn't hunt, it simply is. And what is invites everything else to follow. This is the fear of strange matter, not that it destroys, but that it replaces. That the universe itself may not be built on what's most powerful, but on what's most stable. And if strange matter is more stable than us, then we're just waiting. A brief phase, a passing structure, soon to be something else. When a massive star dies, sometimes it doesn't go quietly. Sometimes it keeps going. It collapses, shrinks, spins, and in the aftermath, a new kind of object is born. Small, heavy, violently fast. These are the fastest spinning pulsars, cosmic engines turning hundreds of times every second. Dead stars, behaving like celestial blenders. A pulsar is a type of neutron star, the collapsed core left behind after a supernova. It's only about 20 kilometers wide, but contains more mass than the Sun. Because of its density, it spins, fast. Like a figure skater pulling in their arms, Conservation of angular momentum causes the star to accelerate as it collapses. Pulsars emit beams of radiation from their magnetic poles. As they rotate, those beams sweep through space. If one crosses Earth, we see it as a regular pulse, like a lighthouse flashing across the sea of stars. Most pulsars spin between 1 and 100 times per second, but then there are the outliers, the millisecond pulsars. These stars rotate at incredible speeds. The fastest known, PSRJ 1748-2446 AD, spins at 716 rotations per second. That's nearly a quarter the speed of light at its equator. To move that fast and stay intact requires an impossible balance. The gravitational pull must be just strong enough to counter the centrifugal force. Any faster, and the star would tear itself apart. These fast pulsars are usually found in binary systems. Over time, the pulsar pulls in matter from its partner, increasing its spin, winding it up like a top. At these speeds, the rules of relativity kick in. The pulsar's rotation drags space-time around it, a phenomenon called frame dragging. Near the surface, time itself begins to warp. Clocks slow, light curves, gravity distorts. Studying these objects allows physicists to probe the limits of matter. Some scientists believe the fastest spinning pulsars might not be neutron stars at all, but quark stars, or even preon stars. Exotic objects made of particles smaller than quarks. These aren't just stars, they're laboratories. Spinning test chambers where the universe reveals its deepest equations, and they are barely stable, balanced on the edge of collapse, where one extra spin might tear the star apart. These are stars that died and kept spinning so fast they dragged time with them, bending the laws of motion and reminding us that the boundary between physics and chaos is thinner than we thought. In the beginning, there was darkness, no stars, no galaxies, no light, just hydrogen and dark matter. But then, something happened. The first stars ignited. The cosmos began to glow. And yet, what if the light didn't come from fire? What if the earliest stars weren't powered by fusion, but by something far stranger? This is the idea behind dark stars. Hypothetical celestial objects that may have burned not with atoms, but with annihilating dark matter. To understand how strange that is, we need to look at what makes a normal star shine. In standard stellar physics, a star forms when a cloud of gas collapses under gravity. As pressure builds, hydrogen atoms fuse into helium, releasing energy. This is nuclear fusion, the process that powers our sun. But in the early universe, just a few 100 million years after the Big Bang, conditions were different. No metals, no complex molecules, just primordial gas, and an abundance of dark matter. According to some theories, if a cloud of gas collapsed in a region rich in dark matter, something new could happen. If dark matter particles can annihilate when they collide, they would release energy to heat the collapsing cloud. So instead of fusing hydrogen, the early star would glow from the self-destruction of dark matter. These objects would still shine, but not like the stars we know. They'd be cooler, larger, and longer-lived. Models suggest dark stars could grow to hundreds of times the size of the sun. They would emit mostly infrared light and drift quietly through space, too dim for early telescopes to detect. But today, our tools are more powerful. The James Webb Space Telescope has begun to peer deep into the early universe. Some of the bright, ancient objects it's seeing don't quite match what we expect. They're too big, too bright, too early. Some physicists now believe we may be seeing the first hints of dark stars, celestial ghosts from a time when the universe was young. If confirmed, it would mean dark matter isn't just passive scaffolding. It may have played an active role in the birth of structure and light. And that changes everything. Because if dark stars really existed, they may still exist today. Ancient, massive, and nearly invisible. Floating through the galaxy, sustained by the quiet annihilation of unseen particles. They wouldn't explode. They might not collapse. They might just persist. What else in the universe might be powered by unseen engines? How many of the stars we think we know are something else entirely? If light once came from darkness, then the story of the cosmos isn't just one of ignition, it's one of transformation, of shadows becoming stars, of the invisible creating everything we see. We expect black holes to be massive, to devour stars, to anchor galaxies. But what happens when one grows too big, too early, too fast? This is the mystery of TON 618, a black hole so massive it defies explanation. Located over 10 billion light-years away, TON 618 lies at the center of a quasar, a brilliantly glowing galactic core powered by an actively feeding black hole. Measurements suggest its mass is around 66 billion times that of our Sun. 66 billion suns collapsed into a single point of gravity. Black holes this large are called ultramassive, beyond the supermassive ones at most galaxy centers. But TON 618 existed when the universe was less than 4 billion years old. According to everything we know about cosmic evolution, there simply wasn't enough time for something this large to form. Even with constant feeding through accretion or mergers, it couldn't reach this size that quickly. Some theorists suggest it may have started from a primordial seed, a black hole born from the direct collapse of a massive gas cloud in the early universe. Others believe TON 618 may be a remnant of physics we don't yet understand, perhaps even a cosmic relic from a universe before ours. Because to grow this large, this quickly requires more than just gravity. It may require new laws of nature. What's more disturbing, TON 618 may not be unique. If true, it would mean the early universe contained hyper-efficient black hole factories, regions producing massive objects far faster than we thought possible. These black holes don't just stretch the limits of mass. They stretch the limits of cosmic memory. What if TON 618 isn't just a massive object, but a scar, a leftover from before the Big Bang, an interloper, a gravitational echo from another reality? The deeper we look into the universe, the more we find things that don't just defy explanation. They laugh at it. TON 618 is one of those things. Too massive, too fast, too soon, and still utterly silent. Watching as we try to understand a cosmos that may already be far stranger than we were prepared to accept. We're taught that black holes are the end of the story, where matter disappears, where time collapses. But what if that isn't the end? What if it's a beginning? A door, a tunnel, a passage? Could black holes be gateways to other universes? This idea isn't just science fiction. It's a serious proposal in theoretical physics, rooted in Einstein's equations. The concept emerged in 1935, when Einstein and Nathan Rosen discovered a solution suggesting a bridge between different regions of space-time. The idea centers on a Kerr black hole, a rotating black hole. In these models, rotation changes everything. Instead of collapsing into a point, the black hole may form a ring-shaped singularity, and within that ring, a tunnel could emerge, a wormhole. Wormholes connect two regions of space-time, like shortcuts through the fabric of the universe. In theory, matter falling into the black hole could pass through and emerge somewhere else, possibly in an entirely different universe. This structure is called an Einstein-Rosen bridge, but it raises a major issue: stability. Wormholes, if they exist, would likely collapse before anything could travel through them. To remain open, they'd require exotic matter with negative energy density, a kind of anti-gravity material we've never seen. Physicists distinguish between traversable wormholes, allowing two-way travel, and non-traversable ones, one-way trips, if possible at all. Hawking's work on black hole radiation suggests information is not truly lost forever. Perhaps it's transformed or transferred. If black holes can birth universes, then every massive star collapse could be creating something new on the other side. This forms the basis of cosmological natural selection, the theory that universes evolve toward greater black hole production. And then, there's the ultimate twist. What if the Big Bang wasn't the beginning of everything, but the other end of a wormhole? We might be living inside the child of another cosmos, born not in silence, but in collapse. Black holes remain our most mysterious cosmic objects, not just for what they destroy, but for what they might create. Perhaps the singularity isn't a prison. Perhaps it's an origin, a cosmic womb. And maybe, just maybe, there's a universe on the other side, wondering where it came from too. We often picture black holes as immovable giants in galactic centers, monsters that stay put. But not all of them stay in place. Some go rogue. They drift. They wander. They vanish into the dark. These are rogue black holes, unbound, invisible, and always moving. And many may be closer than we think. Astronomers first theorized their existence in the 1970s, when simulations suggested some black holes might be ejected from their home systems. A rogue black hole is exactly what it sounds like. A black hole not gravitationally attached to anything. It simply travels through space, alone. How does that happen? Sometimes, a massive star collapses in isolation, forming a black hole far from other systems. Other times, violent events can eject black holes. A supernova, or an encounter with another black hole, can create slingshot effects, flinging the object out of its galaxy. These cosmic outcasts move at astonishing speeds, up to 1,500 kilometers per second. Some drift more slowly, like silent predators through the void. They vary in size. Some are stellar mass rogues, just a few times our sun's mass. Others are intermediate, thousands of solar masses. A few might be supermassive outcasts ejected during violent galactic mergers. Once free, these black holes become nearly undetectable. They emit no light. They have no accretion disks. So, how do we find them? Sometimes, a rogue black hole passes in front of a background star. Its gravity bends the starlight, an effect called gravitational lensing. In 2022, scientists observed what may have been the first isolated black hole ever directly detected. An object 7 times our sun's mass, drifting at 45 kilometers per second. Scientists tracked a star's light as it brightened and dimmed over 270 days. For the first time, we glimpsed one of these wanderers. But that's one, out of many. Estimates suggest the Milky Way could contain millions of rogue black holes. Some may be only a few hundred light-years away, and we'd have no way to see them coming. Future detection methods may improve our chances. Gravitational wave observatories might sense ripples when two rogues collide. If a rogue black hole were to pass through our solar system, it could destabilize planetary orbits or slowly pull planets toward destruction. Studying rogue black holes helps us understand how stars die and how the universe's most extreme gravitational systems evolve. But there's something haunting about them. We tend to imagine danger as something visible, obvious. But rogue black holes don't roar. They drift. They wait. They erase without sound. Out there in the dark, beneath the glow of stars we can see, are travelers we can't. We're taught that the universe is expanding equally in all directions. But what if something is pulling us? Not from inside the universe, but from outside? This is the mystery of dark flow, a strange motion of galaxy clusters, all drifting in the same direction, as if something unseen is dragging them. It began in 2008. Scientists analyzing data from NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, noticed an anomaly. Clusters of galaxies appeared to be moving together. Not just with cosmic expansion, but drifting at speeds between 600 to 1,000 kilometers per second in a single, coherent direction. This motion didn't line up with known gravitational influences or match the distribution of matter in the observable universe. They called it dark flow, because whatever was causing it, we couldn't see it. One hypothesis? Gravitational pull from beyond the observable universe. Massive structures outside our cosmic horizon might still be exerting influence. Think of it like standing in a valley, surrounded by fog. You can't see beyond the hills, but you feel a wind blowing in. In some theories, our universe is a bubble in a vast multiverse. Other universes' gravity could tug on our space-time. Another idea? These structures could predate cosmic inflation, the moment just after the Big Bang when the universe expanded faster than light. But the concept remains controversial. Later observations from the Planck satellite offered less support for dark flow. Some argued the WMAP data reflected a statistical anomaly. Yet, Planck couldn't completely rule it out, and the original signal still lingers, haunting, unexplained, potentially profound. Because if dark flow is real, then the edge of the observable universe isn't the end. It's just a curtain. That something beyond could be other universes, or vast accumulations of mass that formed before known physics began. It challenges the idea of cosmic homogeneity, the assumption that the universe looks the same in every direction. Dark flow may be a mirage, a statistical ghost, or it may be the fingerprint of something greater, a whisper from the outside, a hint that this universe isn't all there is. Imagine it. A current gently pulling billions of galaxies toward a place we can never see. Galaxies are supposed to follow rules, a core of stars held together by gravity, a halo of dark matter hidden but necessary. But what happens when they don't? When a galaxy is missing something fundamental, like stars or dark matter? These are the phantom galaxies, and they shouldn't exist. Astronomers have begun spotting strange outliers. Galaxies that look like galaxies, but behave like something else. Some, like NGC 1052-DF2 and DF4, contain stars, but the way those stars move suggests something disturbing, almost no dark matter. That's not just unusual, it's physically impossible, according to our models. Galaxies need dark matter to stay gravitationally bound. Without it, their stars should scatter. Yet here they are, intact. Meanwhile, other galaxies defy the opposite expectation. We call them ultra-diffuse galaxies, or UDGs. They stretch across hundreds of thousands of light-years, as large as the Milky Way, but with barely any stars. Some UDGs contain as little as one star per 100 light-years. They glow like phantoms, barely visible. And yet, they appear to be packed with dark matter. They are massive, but invisible. Heavy, but hollow. For dark matter-deficient galaxies, some scientists suggest they were stripped by gravitational interactions with neighboring galaxies. For ultra-diffuse galaxies, theories range from failed galaxies to systems stretched by tidal forces to primordial structures. But no single explanation ties it all together. And that leaves us with a deeper question. How many phantom galaxies have we me? Physics is often described as elegant, a dance of particles and forces in symmetry. But symmetry isn't always perfect. Sometimes it breaks. One of the most profound mysteries in quantum theory comes from this imbalance, and the possibility that hidden in reality exists a particle that restores it. A particle so light and elusive that billions could pass through your body right now, and you'd never know. This is the axion, a theoretical particle, and one of the most promising candidates for dark matter. The story begins with the strong nuclear force, the force that holds atomic nuclei together. But there's a problem. The equations that describe this force allow for CP violation. In theory, this should happen, but in experiment, it doesn't. Why? Physicists in the 1970s proposed a missing piece, a ghost particle that would naturally cancel out the violation, restoring symmetry. They called it the axion, named after a laundry detergent because it would clean up the equations. As theorists studied this particle, they noticed something unusual. Axions wouldn't just solve the strong CP problem. They would also fit all the necessary properties of dark matter. They would be electrically neutral. They would interact very weakly with normal matter. And they would be incredibly lightweight. They wouldn't clump or shine. They would drift through stars, through planets, through you. Experiments like ADMX and CASPER are trying to detect axions by their effect on magnetic fields or quantum fluctuations. So far, no confirmed signal. But the search continues. Because if we find them, we may finally understand what dark matter really is. That means answering why the universe weighs more than it shines. Axions could be the missing substance, the quiet framework holding galaxies together. Some theories suggest axions might form Bose-Einstein condensates on cosmic scales, like ghostly waves through galactic halos. In this view, axions don't just exist. They shape the universe without ever interacting with light. They would be the shadow scaffolding of reality. To find an axion would be to glimpse the universe's hidden symmetry. A ghost, a balancing force, a reminder that the world we see is only the surface, and beneath it, threads of something colder, older, quieter, still waiting to be found. We often speak of the universe as infinite, but our view of it is not. There is a limit to what we can see, drawn not by technology, but by space-time itself. That limit is called the cosmic horizon, not a wall, not an edge, not a place we can ever reach. It's the farthest distance from which light has had time to reach us since the universe began, 13.8 billion years ago. But because the universe has been expanding, that distance isn't 13.8 billion light-years. It's about 46.5 billion light-years in every direction. That's the size of our observable universe, our cosmic bubble. Everything within that bubble is causally connected to us. We can see it, measure it. But beyond the horizon, light hasn't had time to arrive. Those places are real, but forever disconnected from us. Even if we could travel at light speed, we'd never reach them, because the space between us is expanding faster than we can cross it. Physicists distinguish between types of horizons. The particle horizon marks what we can currently observe. The event horizon marks what we will ever be able to observe. Together, they form our cosmic prison, our bubble of causality. As cosmic expansion accelerates, driven by dark energy, more galaxies will cross that horizon. They will fade from view because their light will never arrive. In the far future, observers would see a night sky nearly empty of distant galaxies. In time, only our local group of galaxies will remain visible. Everything else will be gone. And yet, those distant galaxies will continue, forming stars, colliding outside our reach. The oldest light we detect is the cosmic microwave background radiation, the afterglow of the Big Bang, from when the universe was just 380,000 years old. But even this defines a horizon. Before it, we cannot see. The cosmic horizon isn't a wall of matter, it's a boundary of causality. It defines the limit of our knowledge, because it forces us to ask, does something exist if we can never observe it? Are there civilizations unimaginably far away that we can never meet, never detect? Is their reality as real as ours, even though no light they emit will ever touch us? Some physicists believe beyond our horizon lies a vastly larger cosmos, maybe even infinite. We may never know. And yet this horizon is not just a limit. It's a reminder that we are tiny observers in a growing sea, watching the stars move away as the light behind them fades. The observable universe is our island. Beyond it, an ocean of silence. And that silence is still getting louder. Imagine two particles born together in the same quantum moment. Then imagine pulling them apart, across miles, across galaxies. Now measure one, and the other reacts. Instantly. No signal, no time delay, just a shift that defies everything we know about distance. This is quantum entanglement. It sounds like science fiction, but it's one of the most well-tested phenomena in quantum mechanics. At its core, entanglement means two or more particles can become so linked that measuring one immediately determines the state of the other, even if separated by billions of light years. This isn't just theoretical. It's been observed over and over again. In the 1960s, physicist John Bell designed a test to prove entanglement was real. When researchers performed these Bell tests, the results were clear. Entanglement exists. Einstein called it spooky action at a distance, because it seemed to violate the rule that nothing travels faster than light. But entanglement doesn't send signals. It doesn't transmit information classically. It simply is, a shared state between 2 points, outside space and time. Now we're beginning to harness this strangeness. Quantum computers use entangled qubits for impossible calculations. Quantum cryptography uses it for unbreakable codes. In the early universe, just after the Big Bang, countless particles were created. Some of those pairs might still be entangled. Particles on opposite ends of the observable universe that remain connected. A quantum link stretching across 93 billion light-years. This raises a question. What does it mean for things to be separate? If entanglement ignores space, then space itself might not be fundamental. Some physicists think space-time could emerge from entanglement, that the geometry of the cosmos arises from the web of quantum relationships underneath everything. In this view, reality is not made of isolated pieces, but of connections, and space is just the pattern those connections make. This is quantum non-locality, the idea that what happens here connects to what happens everywhere else, not through force, through entanglement, a whisper across the cosmos. This challenges our basic assumptions about causality, identity, boundaries. Perhaps the universe is less a collection of separate objects and more a single, unified system. And if that's true, nothing is ever truly alone. Not a photon, not a person, not a galaxy. We live in a universe woven by invisible threads, where separation may be just an illusion, a comforting thought, or an unsettling one. Either way, you're not as alone as you think. We think of crystals as still, atoms locked in a repeating pattern, unchanging in space. But what if matter could crystallize in time? What if structures existed that oscillated endlessly through time without energy or decay? These are time crystals. For years, just a theoretical ghost, a mathematical whisper. But today, they are real. First proposed by Nobel laureate Frank Wilczek in 2012, a time crystal exhibits motion in its lowest energy state. It doesn't sit still. It cycles, forever repeating. In classical physics, this shouldn't be possible. Systems at their ground state, the state of lowest possible energy, should stop moving. But in quantum physics, things are different. In 2021, researchers at Google created a time crystal using their quantum computer. They observed a system falling into a rhythm, a time-locked loop that persisted without energy loss. It didn't behave randomly. It didn't decay. It moved with purpose, then returned, over and over. This isn't perpetual motion. The system isn't creating energy or violating thermodynamics, but it's breaking time translation symmetry. That's a fancy way of saying it behaves differently, depending on when you look at it. The laws of physics, in almost every situation, don't care about time. But time crystals? They respond to time. They dance with it. And this opens a door. If matter can repeat in time the way it repeats in space, then time may not be as linear as we believed. Maybe time can freeze. Maybe it can loop. Maybe it can be structured. In the lab, time crystals remain small, fragile, but their existence rewrites what phases of matter can be. Their future may include quantum systems that never degrade, perfect clocks, logic gates without heat, or something stranger, a new way to build with time. In a universe ruled by entropy, where everything decays, time crystals rebel. They refuse to decay. They spin at reality's edge, whispering a new kind of motion, one that never dies. Imagine matter that doesn't just exist in time, but remembers it and uses it to stay alive. We take comfort in the rules of the universe, that atoms will behave the same tomorrow, that gravity will still pull, that existence itself will continue. But what if everything, every law, every particle, every thread of reality, balances on a fragile illusion? This is vacuum decay. And if true, the universe could end not with a bang, but with a silent, quantum sigh. In quantum field theory, space isn't empty. It's alive, woven with invisible fields, rippling with virtual particles, blinking in and out of existence. These fields settle into a vacuum state, a configuration of lowest possible energy. But here's the problem. What we think is the lowest energy state might only be metastable, like a ball resting in a valley, unaware that a deeper valley lies beyond a ridge. And if something pushes it over that edge, a bubble of lower energy vacuum could form, expanding at the speed of light, consuming everything. Nothing would survive. No warning, no escape, no trace. This is vacuum decay. The universe spontaneously transitioning to a truer form, one governed by different physics. A new vacuum state where matter as we know it can't exist. Not an explosion, not fire, not sound. Just change. Instant. Complete. Calculations involving the Higgs field, especially after the Higgs boson discovery in 2012, suggest our universe might indeed be metastable, balanced precariously, not doomed, but uncertain. The mathematics show the Higgs field, which gives particles mass, sits in delicate balance, like a pencil standing on its tip, and quantum fluctuations, tiny ripples in reality's fabric, could eventually tip it over. Physicists estimate this cosmic transition might happen in 10 to the power of 100 years. A number so vast, it defies imagination. Time enough for countless civilizations to rise and fall, for galaxies to be born and die, or it could happen tomorrow. Because in quantum mechanics, even the most improbable event can happen. Eventually. This doesn't mean it will, but it could. And the end may come not from without, but from within. Some cosmologists wonder if we might detect signs of this instability, perhaps in the coldest, emptiest parts of space, where quantum fluctuations grow largest, where the veil between states is thinnest. But like listening for a whisper in a hurricane, such signals would be nearly impossible to hear. Take a moment to reflect. Most apocalyptic theories involve stars exploding, planets colliding, entropy running its course. But vacuum decay is different. It is reality folding in on itself. The laws of physics rewritten mid-sentence. The canvas erasing itself, while the painting remains unaware. And the most disturbing thought? We could already be inside it, because the bubble travels at light speed, and nothing outruns light. No signal comes before it. No moment happens after, just the now, and then nothing. We live with faith in a stable cosmos. But the truth is, we might be guests in a house that was never finished, and the floor beneath us, it only pretends to be solid. Yet perhaps there's comfort in this cosmic fragility, that something so vast could share our vulnerability, that the universe itself might understand what it means to be temporary. Some theories predict the universe will end in fire, a grand collapse, a final explosion, a rebirth in chaos. But the most widely accepted theory is quieter, slower, far more haunting. It's called the heat death of the universe. Not a violent end, but a cosmic whisper, a fading into silence. Heat death is rooted in thermodynamics, especially the second law, which says that in a closed system, entropy always increases. Entropy is disorder, gradual loss of usable energy, and the universe is the ultimate closed system. As time marches on, energy spreads out. Temperature differences vanish. Stars burn through their fuel. Black holes slowly evaporate. Galaxies drift apart. Eventually, nothing will remain that can do anything. No heat flow, no life, no change. The universe will reach thermal equilibrium, a state where all usable energy is gone, and particles are so distant that interaction becomes impossible. This won't happen tomorrow, or even in trillions of years. This is the longest silence imaginable. In the next few billion years, the last stars will exhaust their fuel. Some will explode. Others will collapse into white dwarfs or black holes. Over the next trillion years, the sky will darken. New stars will stop forming. The last red dwarfs will blink out. The black hole era will follow, lasting perhaps 10 to the power of 100 years, a number exceeding all atoms in the universe. Even black holes will eventually evaporate through Hawking radiation, leaving only faint radiation, dead particles, and an expanding void. Eventually protons themselves may decay, dissolving all matter into subatomic dust. No atoms, no light, no heat, just the stillness of entropy. A universe that cannot change, a place where time loses meaning, because change defines time, and there will be none. Some seek hope in this future, that a random quantum fluctuation might spark a new universe, that from infinite stillness a spark might return. But these are speculations, not solutions. In the heat-death scenario, there is no final explosion, no cosmic reset, no violent apocalypse, just a gradual, relentless fading. It is not a fire, it is ash, without even flame. The stars do not scream, they do not burn, they go cold and vanish. and the universe becomes something like a ghost, not dead, but beyond decay, a place where nothing happens because nothing can. Take a moment to reflect on this. The most likely fate of the universe is not chaos, it is not fire, it is not war, it is quiet, and it will last forever. You remember your childhood, the sound of laughter, the feeling of warmth, a sky full of stars. But what if none of it ever happened? Not because it was a dream, but because it never existed at all. What if you never existed at all? This is the Boltzmann brain paradox, a thought experiment questioning the very nature of existence, memory, and reality. It begins with Ludwig Boltzmann, a 19th-century physicist who helped develop statistical mechanics, the science of entropy and probability in physical systems. He imagined a universe governed by randomness and thermodynamic rules. In such a universe, drifting toward maximum entropy, where all order dissolves, rare fluctuations can occur. Given enough time, improbable things happen. A particle here, a molecule there, occasionally, something complex, a planet, a star, a mind. Statistically, it's far more likely for a single brain to randomly assemble from chaos, fully formed, with false memories of an entire lifetime, than for an ordered universe to spontaneously appear. This is the paradox. If we trust probability alone, it's more likely that you are a disembodied mind, floating in a void, hallucinating everything around you, than a conscious being in a genuine universe. That's the Boltzmann brain, a consciousness appearing out of nowhere, remembering a life that never happened, vanishing without a trace. It's not science fiction. It's a logical consequence of certain cosmological models, especially those involving eternal inflation or the heat death of the universe. If the universe is infinite and eternal, rare fluctuations must occur, and among them, Boltzmann brains will vastly outnumber real, evolved minds. But if that's true, how can we trust anything? How can we be sure we're not just one brief, isolated flicker, a mind untethered to reality, dreaming a life that never was? This thought terrifies physicists and philosophers alike, because if Boltzmann brains are common, then we are not. Our very experience of consistency, of cause and effect, of history, of memory, becomes statistical noise. To escape this paradox, some theories propose that the universe isn't infinite, or that vacuum fluctuations can't sustain consciousness, or that cosmological decay occurs too quickly for brains to form. But none of these explanations are fully proven, and the question remains: if you opened your eyes in a void, no stars, no time, no past, but believed with all your heart that you had lived, would it matter that you hadn't? Would the illusion be any less real? Take a moment to reflect on this. The Boltzmann brain isn't just a question about physics. It's a whisper of doubt that cuts through reality itself. And if you are a Boltzmann brain, you won't be here much longer. You'll vanish, and the void will forget you, as if you never were, because maybe you never were. We look up at the night sky and imagine ourselves in the universe, floating in its vastness, peering out. But what if we're not in it at all? What if we're inside something else entirely? A black hole, a cosmic boundary, an event we can't escape, because we've already passed the point of no return. It sounds absurd, but mathematically, it might make sense. Black holes form when enough matter collapses inward, compressed until gravity becomes inescapable. The outer boundary is called the event horizon. Once crossed, nothing, not even light, can return. To an outside observer, the collapse appears to slow, freeze, then vanish. But to the matter inside, time continues, space expands. Now flip this idea. What if the Big Bang wasn't an explosion outward, but the inward collapse of another universe's matter? A gravitational implosion that created a new, expanding region, sealed behind its own horizon. Some physicists believe our universe could be just that. A black hole formed inside a higher dimensional cosmos, its boundary hidden beyond our reach. From our perspective, we see only an expanding universe, one that began in fire and now accelerates into darkness. But from another frame, we might be falling inward. The geometry checks out. The same equations that describe our expanding universe, the Friedmann equations, mirror those that define a black hole's interior. Under certain models, the curvature of space, the presence of a horizon, and the entropy of the cosmos all match a black hole's interior traits. That horizon could be what we call the cosmic boundary, a limit to what we can see, not because of light or distance, but because we're enclosed. And this leads to a deeper possibility. If we live inside a black hole, then everything we know, galaxies, particles, even time itself, might be a holographic projection on the boundary, an encoded shadow of a greater reality beyond. You've heard of the holographic principle, that all information within a space could be stored on its surface. Well, what if our universe is the inside of that surface? Not infinite, but curved. Not outside the black hole, but within its walls. Physicists like Nikodem Poplawski and Lee Smolin have explored this possibility for decades. Their mathematics suggests that when matter collapses beyond a critical threshold, it doesn't simply disappear. It transforms. It creates a new region of space-time, a child universe, branching from its parent. This would explain the cosmic balance we observe, the delicate tension between expansion and entropy. Why our universe seems so finely tuned for existence. It inherits properties from what came before, like cosmic DNA passed to the next generation. Some astronomers point to anomalies in the cosmic microwave background, those ancient echoes of creation, as possible evidence of our universe's black hole parentage. Whispers from beyond our horizon. We wouldn't know. We couldn't know, because our space-time would be shaped by that containment. Every measurement, every observation would come from within the event. No way out, no edge to find, no wall to crash into. Just a silent, relentless expansion. A black hole turned inside out. And you? You've never been outside it. Not for a moment. You were born inside the event horizon. You lived your whole life beneath its surface. And someday, you'll return to it. When we speak of black holes, we often speak of endings. An end to light, an end to matter, an end to the known laws of physics. At the center of a black hole, it's said, lies a singularity, a point of infinite density where space-time tears itself apart. But what if the singularity doesn't exist? What if it's not a void, but a seed? Some physicists believe that at the very core of a black hole, there is something else, something real, something dense beyond comprehension, yet finite. They call it a Planck star. The idea comes from a framework known as loop quantum gravity, a theory that reimagines space-time not as a smooth fabric, but as a network of interwoven loops. Tiny, discrete, quantized, fundamental. According to this theory, when a star collapses under its own gravity, it compresses until the density reaches the Planck scale, a threshold so extreme that quantum pressure resists further collapse. Gravity and quantum mechanics push against each other, and instead of a singularity, something else forms, a Planck star, a core of unimaginable density where time nearly stops. To us, from the outside, the black hole looks as it always has, a silent shadow, a gravitational trap. But inside, time behaves differently. Near the event horizon, the flow of time slows dramatically. What seems like billions of years to an outside observer might pass in mere seconds from within. And eventually, as the black hole evaporates through Hawking radiation, shrinking over unfathomable timescales, the Planck star rebounds. It explodes, not violently, but cosmically, releasing all the matter and information the black hole ever consumed. Not lost, not destroyed, returned. A cosmic exhale after an eternity of silence. Some physicists believe these events may already be happening. That certain unexplained gamma-ray bursts in deep space could be the final size of ancient black holes, Planck stars reaching their breaking point and releasing their long-held contents into the void. If true, this would solve one of physics' greatest puzzles, the information paradox. It would mean that nothing is truly lost in a black hole, only delayed, only compressed, until the moment of release. It also reframes our understanding of time. Within the event horizon, time may stretch so slowly that what seems eternal from our perspective is a blink inside. A Planck star could already be exploding. We're just waiting for the light to reach us. This isn't just a scientific idea, it's a metaphysical one. That collapse is not the end, that beneath even the most hopeless gravity, there may still be structure, memory, a countdown. A Planck star is not a singularity. It is a pause, a held breath in the heart of darkness. And when it exhales, the universe may remember everything that ever fell in. Imagine the silence before time. No stars, no matter, not even space. Only a strange stillness, and perhaps a sound. Not a sound in the way we understand it, but a ripple in the fabric of being itself. A memory that predates memory. A wave from before the beginning. We call them gravitational waves, ripples in space-time caused by the violent dance of massive objects, colliding black holes, collapsing stars. They stretch and squeeze the universe as they pass, subtle but real. And in 2015, we heard them. The Laser Interferometer, Gravitational Wave Observatory-LIGO- recorded a signal. Two black holes had merged over 1 billion years ago, and the vibration finally reached us. A whisper from deep time. But now, scientists are listening for something deeper still. Something from before the Big Bang. The Big Bang has long been considered the beginning, the birth of space, time, and matter. But certain cosmological models tell a different story. They suggest that the universe didn't begin. It bounced. In loop quantum cosmology, space-time isn't smooth. It's made of tiny, discrete loops at the Planck scale. Under immense pressure, those loops resist collapse. Instead of a singularity, we get a rebound, a cosmic reset. And with that bounce comes energy, enough to send ripples through space-time. Gravitational waves from before the Big Bang. They would be unlike any we've observed, not the high-frequency bursts of black hole mergers, but low, slow, cosmic sighs, spread over billions of light years. Ancient pulses, stretching through the void. Detecting them is no small task. Ground-based detectors like LIGO can't hear them. We need something vast, like LISA, the Laser Interferometer Space Antenna. 3 spacecraft floating in a triangle, millions of kilometers apart, listening to the deep bass notes of the cosmos. If these waves exist, if we find them, then the Big Bang was not the beginning. It was simply a page turn. We would be living in a universe with memory, a universe that once collapsed, then bloomed again, and maybe This cycle has happened more than once, each cosmic breath leaving behind an echo, each echo leaving a fingerprint on space-time. It also opens the door to other possibilities, extra dimensions folded into the background, or quantum remnants from a multiverse long forgotten. Waves that crossed universes, bringing messages from realities we'll never see. We may never detect them. The signal may be too faint, too stretched, or too different from what we expect. But even the possibility changes everything. It reminds us that time is not a line, but perhaps a loop, or a spiral, or a heartbeat. And one day, if we listen closely enough, we may hear the breath of a world that existed before the first second ever ticked. A ripple, riding the silence, from a time when silence was all there was. There's a law etched into the bones of the universe, a boundary no object has ever crossed. No rocket, no beam, no signal, not even thought itself, can travel faster than light. Why? Why does the cosmos place this ultimate speed limit on everything that exists? The speed of light in a vacuum, roughly 299,792 kilometers per second, isn't just fast. It's foundational. It's the speed at which causality itself is preserved. According to Einstein's theory of special relativity, as you push something closer to light speed, strange things happen. Time slows, mass increases. The energy needed to keep accelerating skyrockets toward infinity. At light speed, an object's mass would be infinite, and infinite energy is not available. But this is more than a mechanical constraint. It's not just a cap placed on speed. It's a limit woven into the very geometry of reality. You see, space and time aren't separate. They are fused into a single fabric, space-time. And the speed of light is the seam that holds that fabric together. It defines how space stretches, how time flows, and how events relate to one another. If something could move faster than light, it could, at least mathematically, arrive at a destination before it departed. Cause would follow effect. Time would unravel. The speed of light is the boundary between what is reachable and what is forever lost beyond causality. But the mystery deepens. Why is this limit exactly what it is? Why that number, that speed? No one knows. Physicists can tell you how it works, describe its effects, and prove its invariance in every experiment. But the why remains untouched. Even the universe itself seems to twist around the rule. Distant galaxies, carried by the expansion of space, are receding from us faster than light. They're not breaking the rule. They're passengers on a stretching fabric. It's not the galaxies themselves that are moving fast. It's the space between that's growing. Some theorists have dreamed up tachyons, particles that would always move faster than light. But they would come with impossible consequences: imaginary mass, reversed time, and broken causality. So far, we've seen no trace of them. Then there's quantum entanglement. Two particles, light years apart, somehow linked. When one is measured, the other reacts instantly. But this doesn't send messages. No information is passed faster than light. The mystery remains, but the boundary holds. So why this limit? Why a speed that's both barrier and bridge? Perhaps it's a safeguard, a cosmic firewall ensuring that reality unfolds with logic. Perhaps it's an artifact of deeper laws we haven't yet uncovered. Or maybe it's a sign that time, space, and motion are not truly independent. They are one dance, governed by a single rhythm. And that rhythm is set to the speed of light. Why does the universe exist? Not the stars, not the planets, not even space-time itself, but anything. Why is there something instead of nothing? It's a question older than science, older than philosophy even. A question that sits quietly behind every other question we've ever asked. And no one, not physicist, philosopher, or priest, has ever answered it with certainty. Because nothing is not simply emptiness. Nothing is the absence of everything. No particles, no laws, no time, not even the possibility of something. So then, why isn't that what we see? Why do we find ourselves in a vast, ordered universe? Why is there a world where atoms assemble, stars ignite, minds awaken? Some physicists suggest the universe may have come from a quantum fluctuation, an unpredictable, spontaneous blip in a sea of perfect nothingness. Just a flash. And then, space, matter, energy. But if that's true, what gave rise to the fluctuation? Why were the conditions there to allow it? Why should nothing give birth to anything at all? Others propose that the universe is a mathematical inevitability, that in the set of all possible structures, existence simply had to emerge, that the laws of logic, or symmetry, or necessity created reality. But even that moves the mystery back a step. Why is there logic? Why is there necessity? Why should possibility exist if there is nothing to host it? The Big Bang doesn't help us here. It's a description of how the universe expanded, not why it began. It explains what happened next, not what happened first. And so we're left with one of the most haunting silences in all of cosmology. Nothingness is not unstable. It is not noisy. It is not waiting. And yet, it did not persist. Something interrupted it, and we don't know how or why. Some philosophers argue that nothing is an incoherent concept, that non-existence itself may be impossible, that something must exist, always, necessarily. But even this is not satisfying, because why should existence be necessary at all? Why should anything be? Take a moment to reflect on that. Not how things work, but why there's a stage for anything to happen on in the first place. Maybe this question is unanswerable, not because it's too complex, but because it sits outside the boundaries of reason. Perhaps the universe exists not because it had to, or was created, or emerged from anything else, but because it does. Existence may be a brute fact, needing no cause, offering no justification. And yet, doesn't that feel incomplete? Some part of us demands more. That same part that looks at the stars and asks not just how far they are, but why they're shining at all. Why are you here now, watching this, thinking this, being this, in a universe with no obligation to exist? You do. That may be the greatest mystery of all, that there is not nothing, but everything, and no one knows why. Imagine intelligent beings living all around us, so close we could almost touch them, yet forever hidden from our sight. They exist beyond walls of perception, occupying dimensions we can't even begin to understand. What if the cosmos isn't empty, filled with civilizations thriving in unseen realms, just outside the limits of our senses? Our daily reality unfolds in 3 spatial dimensions and 1 dimension of time. It's the fabric we understand, the only world we've ever known. But according to modern physics, especially string theory and theories involving extra-dimensional spaces, our universe might include more dimensions, hidden and tightly curled up at scales far too small or too complex for us to detect. If life evolved in these higher dimensions, it would be as invisible to us as we would be to creatures confined to a flat, 2-dimensional plane. To a 2-dimensional being, we 3-dimensional humans would appear as strange, impossible shadows, or disconnected shapes. Similarly, higher dimensional beings moving through our world might manifest as unexplained phenomena, strange distortions of gravity, unexplained flashes of light, or even impossible motions. These beings would not just be invisible, they would interact with reality in ways utterly incomprehensible to us. Imagine an alien species able to step effortlessly between distant points in space, as easily as we cross a room. Or beings whose forms extend simultaneously across multiple points in space and time, perceiving past, present, and future as a single, unified landscape. If higher dimensional life truly exists, our search for extraterrestrial intelligence must fundamentally shift. The silence we've encountered, the apparent emptiness of space, might not be evidence of solitude, but rather proof that we're searching the wrong way. Our radio signals and space telescopes could be primitive attempts to detect beings whose existence transcends such simplistic technologies. The implications go further, into the heart of how we define life and consciousness. Higher dimensional civilizations might not simply be technologically advanced. They might embody entirely new forms of biology, consciousness, and existence itself. We would have to confront profound humility, recognizing that our intelligence is bound by our dimensional limits. From their vantage point, these beings might see us clearly, understanding our struggles, our science, our very essence, while we remain blind to their presence. Perhaps these mysterious beings occasionally reach into our realm, subtly guiding events or simply observing quietly from their elevated perspective. The universe might not be a silent void after all, but a richly inhabited tapestry, alive with civilizations we are inherently unable to perceive. Maybe, just beyond our senses, an interdimensional cosmos thrives, waiting patiently for humanity to awaken to its presence. And as we peer into the darkness, seeking signs of life, perhaps they're looking back, seeing us clearly, silently hoping that someday, somehow, we'll finally see them too. There are moments where fate seems sealed, where death feels like a certainty, inevitable and final. And yet, what if, from your perspective, it never arrives? This is the paradox of quantum immortality, a theory where death becomes not an end, but an illusion. Proposed in the late 1990s by physicist Max Tegmark, this thought experiment emerged from quantum theory, probing the nature of observation itself. It begins with the many worlds interpretation of quantum mechanics, introduced by Hugh Everett III in 1957, suggesting that every possible outcome isn't just a possibility, but happens, each in a new branch of reality. In one branch, the dice land snake eyes. In another, they don't. The universe splits, and both outcomes live on. Consider the quantum suicide machine. A device measures a particle's spin. If it spins up, you live. If down, it instantly ends your life. With each trigger pull, the universe branches. In branches where the particle spins down, observers see you perish. But you only ever experience the branch where you survive. Now imagine your life depends on a quantum event, a radioactive atom's decay, determining whether you live or die. In the world where the atom decays, you perish. But in the world where it doesn't, you survive. And according to this theory, you only ever experience the worlds where you survive. To outside observers, you're gone. But from your point of view, the story continues. You always wake up. This connects to the anthropic principle. Observations of the universe must be compatible with the conscious life that observes it. Even if survival becomes increasingly improbable, even if the body breaks, You continue down the path where consciousness remains, a flicker of awareness, endlessly delayed from non-existence. Many scientists remain skeptical. Roger Penrose suggests consciousness isn't just a passive observer riding quantum waves. Others argue that you, in each branch, might effectively be a different being. This is not immortality of legends. It's survival by default. Because the version of you that could experience death never does. It's a mind forever skipping to the branch where life goes on, one heartbeat to the next, no matter how fragile or unlikely. But this raises a haunting question. Where does that thread eventually lead? What if each new branch is lonelier, more broken, more distant from the world you once knew? What if you outlive everyone? Philosophers like David Lewis question whether these parallel lives hold meaning. Is a self stretched across infinite branches still a self at all? Quantum immortality isn't a promise. It's a prison, built from statistical persistence. You wander an eternal forest of consequences that no one else remembers. From your perspective, death never comes. But perhaps nothing else does either. You exist until existing itself becomes the strangest outcome of all. Time feels like a current, pushing forward, sweeping everything from past to future. But what if that current only flows in one direction? Here. Some physicists believe our universe may have a mirror twin, one that began with us at the Big Bang, but runs backward in time, not metaphorically, literally. A universe where everything unfolds in reverse. This idea finds its roots in one of the most fundamental symmetries in physics, CPT symmetry. It states that if we simultaneously flip charge, parity, and time, the laws of physics remain unchanged. Charge reversal turns particles into their antimatter counterparts. Parity creates mirror reflections of spatial dimensions, and time reversal makes processes run backward, like a film played in reverse. These transformations, applied together, leave the mathematical structure of our physical laws intact. If this symmetry holds across the cosmos, it suggests a radical possibility, a CPT mirrored twin, a universe of antimatter arranged in reverse geometry, flowing backward in time. In 2020, physicists led by Neil Turok, Latham Boyle, and Kieran Finn proposed such a universe might have emerged alongside ours in a time-symmetric Big Bang. Instead of a single universe branching forward, two emerged, mirror reflections moving in opposite temporal directions. Before this theory, most cosmologists imagined our universe bursting from a singularity. But in this alternative, the singularity isn't a beginning or end. It's a pivot point, a cosmic mirror where time itself reflects. In this model, the past and future aren't endpoints. They're balanced extensions. What looks like expansion and aging to us might look like contraction and youth to someone there. The implications cascade through physics. Entropy, the measure of disorder that increases in our universe, would decrease in the anti-universe. Their arrows of causality would point in opposite directions. Events that appear random to us might be determined by future conditions in their frame. This anti-universe wouldn't just run backward, it could solve enduring puzzles. The imbalance of matter and antimatter, balanced across both. The nature of dark matter, potentially explained as mirror particles bleeding across the cosmic divide. The theory even offers an elegant explanation for cosmic inflation. Rather than requiring extra fields or forces, it emerges naturally from the mathematics of reflection. But more than that, it reframes time itself, not as a universal arrow, but as a relative direction. From the anti-universe's view, We are moving in reverse. The moments we call history might be their distant future. Could our lives, thoughts, and galaxies be echoed, inverted, and played in reverse across a hidden horizon? We'll likely never see this anti-universe. It lies beyond what we can measure, but the math whispers of its symmetry. The theories leave space for its shadow. And if it's real, then somewhere in the mirrored silence, the universe is already unhappening. When the universe was just a heartbeat old, reality itself was unstable. It wasn't a place filled with stars and galaxies. It wasn't even space as we know it. It was a seething, high-energy plasma where forces, gravity, electromagnetism, the strong and weak nuclear forces, were still tangled together. Then, something shifted. As the universe expanded and cooled, these forces began to separate, crystallizing into distinct laws of nature. But in that chaotic process, some physicists believe the symmetry didn't break cleanly. It left behind scars, sharp, high-energy defects embedded in the fabric of space-time itself. They are called cosmic strings. Imagine a crack in ice as it freezes. The water turns solid, but not perfectly. Thin fault lines form where the molecules didn't align. Cosmic strings, if they exist, are the cosmic equivalent, infinitesimally narrow, yet astronomically long. They could stretch for billions of light years, thinner than an atomic nucleus, yet more massive per centimeter than Mount Everest. They are not strings in the ordinary sense. These are not physical threads floating through space. They are space, wound tightly and violently, warped by energy densities we can scarcely imagine. A single string could warp gravity so intensely it would act like a knife through space-time, bending light around it, creating optical illusions, gravitational lensing, or duplications of galaxies. And yet, we've never seen one. Scientists have searched the cosmic microwave background for disruptions caused by strings slicing through the early universe. We've looked at gravitational wave data for evidence of cosmic string loops snapping like cosmic rubber bands. Some anomalies have raised eyebrows, but so far, nothing definitive. Still, the math is compelling. Cosmic strings fall out of grand unified theories, models that aim to connect all the known forces. Their existence would validate ideas from the dawn of physics and offer a glimpse into what happened before the first particles had mass. Some might be closed loops, spinning and shrinking, releasing energy as gravitational waves. Others could form tangled networks, drifting across the cosmos, until one passes through a star, or a planet, or a galaxy. If a cosmic string were to pass near Earth, we might witness something strange. A sudden gravitational ripple, a duplication of stars, or a warping of time. If one passed through us, we might not survive, or even notice. It could be over in less than a second. The world would split, ever so slightly, and rejoin behind the passing thread. To some, this sounds like science fiction. But in cosmology, scars matter. They tell us what happened, where the breaks were, where something failed to heal. Cosmic strings may still be out there, drawn taut across the dark, cold stretches of space, waiting, invisible. Proof that even the universe has its fractures. And somewhere in the silence between galaxies, they may still be trembling. You walk forward. You reach out. You feel the space between yourself and everything else. Depth, distance, shape. You know that you exist in 3 dimensions, and time flows steadily forward. But what if all of that, your movement, your sensations, your thoughts, isn't taking place within a 3-dimensional space, but is instead being computed or projected from somewhere else? This isn't just science fiction. It's a serious question in modern physics, and it's called the holographic principle. At its core, the holographic principle suggests something astonishing: that everything within a volume of space, every star, planet, particle, even every moment of your life, can be fully described by information encoded on the boundary of that space. Imagine a cosmic screen surrounding the universe, and everything we think is real being patterns written on that surface. The origin of this idea lies in the study of black holes. According to Einstein, if something falls into a black hole, it's gone forever. But quantum mechanics says information can never truly be lost. This contradiction led to the black hole information paradox. To resolve this, physicists like Gerard 't Hooft and Leonard Susskind proposed a solution. The information swallowed by a black hole isn't destroyed. It's stored on its surface, the event horizon. The three-dimensional contents encoded on a two-dimensional shell. Building on this, in 1997, physicist Juan Maldacena showed that a universe with gravity in 3 dimensions could be perfectly described by a gravity-free quantum theory on a 2-dimensional boundary. This is known as the AD-SCFT correspondence, the first concrete realization of the holographic principle. Some physicists believe this may apply to our entire universe. That reality is a kind of projection, a 3D illusion rising from 2D quantum information inscribed on a cosmic horizon we will never reach. In this view, space and time themselves are not fundamental. They are emergent, like a mirage or a ripple in a pond. They arise from something deeper, something flatter. And if that's true, then you, your thoughts, your memories, your identity, may also be part of this projection. Not that you're fake, but that your existence is information flowing from the boundary of reality. This doesn't mean the universe is meaningless. It may mean that information is the foundation of all things, that reality's fabric is not particles or waves, but bits. It suggests that reality itself is relational, how information interacts, not what it's made of. And it raises the possibility that our universe is just one possible encoding, one image in a gallery of cosmic projections. The holographic principle doesn't say the world isn't real. It says realness itself may be a shadow, cast from somewhere else. And when we reach out into space, into time, into thought, we may be touching the surface of a deeper truth, one written not inside the universe, but on its edge. For centuries, humanity has explored the universe by breaking it down: particles, equations, patterns in the stars. Every discovery brought new questions. Every answer peeled back another layer. And we believed, with enough time, we'd uncover it all. That the universe was a puzzle, and physics was the key. But what if we're reaching the edge? Not the edge of space, not even time, but the edge of understanding itself. This is the unsettling idea some physicists now entertain, that we may be approaching the end of physics, not because we've solved everything, but because we may not be able to go any further. There are a few reasons why. The first is technological limits. To probe the smallest scales of reality, to see what lies beyond the standard model or unify gravity with quantum mechanics, we'd need particle accelerators unimaginably powerful, machines the size of planets, or even larger. The second is empirical silence. Many of our most elegant theories, string theory, the multiverse, loop quantum gravity, are mathematically rich but untestable. They describe possible realities, but offer no concrete predictions we can measure. They may be beautiful, but also beyond reach. And the third reason is perhaps the most sobering. What if there's simply nothing left to find? Some physicists suggest the laws of nature might be the final layer. The standard model works, general relativity works, but they won't unify, and maybe they can't. Perhaps reality isn't endlessly deep. Perhaps it ends not in complexity, but in completeness. If true, we may already be standing at the edge of the map, with no more terrain to chart. This strikes at the heart of our philosophical identity. For generations, we believed that truth was accessible. The end of physics would mean accepting something profoundly humbling, that there may be truths we can never reach, that some questions might not have answers we can find. It would not be the end of knowledge, but a change in how we pursue it, a shift from certainty to mystery. And yet, there is beauty in that. The universe may still speak to us, even if we can't decode every word. The stars may still burn, even if we can't explain why the spark exists at all. Perhaps, when physics reaches its limits, we will return to deeper questions, not just how the universe works, but why it exists, not what laws govern it, but what meaning it carries. Maybe the end of physics is not an ending at all. Maybe it's a pause, a soft moment of reflection, before the next kind of exploration begins. Not with instruments, but with wonder.